Hello everyone, welcome back to AA Academy. So without wasting time, let's continue the model question paper of Introduction to Electrical Engineering, Module 4, question number 8. Okay, so look into the questions. Question number 8A, explain the various losses in a transformer and how to minimize them. Asked it for 8 marks. And also they asked you to explain a rotating magnetic field for 6 and one problem for 8 marks. So anyhow, let's solve the problem. And for the theory, I'll just share the explanation that how much you can able to write in the examination. So just refer this and you can take the screenshot and this will be more than sufficient to write in the examination. Okay. So explain the various losses and how we can able to minimize them. So there are two main losses in transformer. One is core loss, other one is copper loss. So core loss. Core is nothing but it is made up of iron in a transformer, whereas iron losses mainly occurs through the alternating flux. Whenever supply if you are giving to the primary winding of the transformer, and it starts to produce the alternating flux, and it travels in a core, magnetic core, whereas the core which is made up of iron. So due to that continuous flow of alternating flux, the core gets heat. So that loss or that heat dissipation is called core loss. Whereas core which is made up of iron, so that you can also call this as iron loss. And these losses mainly depending on the magnetic material properties of core. So it is having two types of core losses. First one is hysteresis loss. The loss which produces due to the hysteresis effect in the core is called hysteresis loss. It is nothing but whenever a supply which is given to the primary winding, core will get the properties of the magnetizing and demagnetizing. Due to this, net loss dissipated in the form of heat is called as hysteresis loss, and it is given by pH equals to Km and Bm to the power P, whereas P which is varying from 1.5 to 2.5. In between these values you can enter F into V, whereas V is nothing but volume of the core and in terms of meter cube. At the same time, Km is nothing but hysteresis loss constant, and this loss constant which is varying from 0.001 and 0.025 for silicon and cast steel. And you know that B is nothing but flux density. Okay. And how can you reduce the hysteresis loss? So with refer to this equation, you can observe. So pH equals to Km into Bm to the power P stands for 1.5 to 2.5. So with the help of this, you can understand like how we can able to reduce the losses. Okay. So the losses which you can reduce by minimizing the volume of the core. By minimizing the volume of the core, you can reduce hysteresis loss. Okay. Similarly, so eddy current losses. So eddy current loss is nothing but the core of the transformer is made up of high-grade silicon steels and which are laminated and pressed together to form a core. Hence, a core limb will induces their own EMF in each when subjected to alternating flux. So it produces it produces circulating current. So that results in heat dissipation. That is called power loss in the form of heat is called as eddy current loss. And this is given by PE equals Kn into Bm square into F square T square V, whereas Kn is nothing but eddy current constant, Bm is maximum flux density, F frequency, T thickness, V is volume in the core. So how can you reduce the eddy current loss now? By minimizing the thickness of the core, you can reduce the eddy current loss, where the frequency and flux density of the core remains constant. Therefore, you can also call these iron losses as constant losses. Okay, let's move on to the next loss, that is copper loss. Whereas the windings of the transformer, which are made up of copper, so due to the presence of resistance in both winding, heat is dissipated. So that is called copper loss. And it is also known as ohmic losses, sometimes I square R losses. So that total copper loss, which is given by copper loss in primary winding plus copper loss in secondary winding. Whereas primary represents 1 and second represents 2, so that a total copper loss is given by I1 square into R1 plus I2 square into R3. So you can write the total copper loss by referring primary winding or by referring secondary winding, so that you can write I1 square into R1, that is R0 1, whereas R0 1 is equivalent resistance referred to primary winding. Similarly, R0 2 is equivalent resistance referred to secondary winding. So that copper loss, which is directly proportional to the square of the current, and also you can call this copper loss as variable losses. So there are two losses in transformer. First one is constant loss or copper loss, sorry, constant loss or iron loss or core loss. And the second one is copper losses. You can also call this as variable losses. And in the core losses, there are again two main types. One is hysteresis loss and the one is eddy current loss. Let's move on to the second portion. So with the diagrams, you need to explain rotating magnetic field. First, you should understand what is RMF, that is what is rotating magnetic field. The rotating magnetic field is nothing but whenever the magnetic field having a constant magnitude but continuously changing its direction. A field which has a constant magnitude but it changes its direction is called rotating magnetic field. So whenever three-phase supply, if you are giving to the induction motor, whether the stator which is connected in star or delta, so it produces three different fluxes, phi R, phi Y, phi B. Three fluxes it produces. So all the three fluxes are having the phase difference of 120 degrees, so that from phi R to phi Y, it has 120 degree phase difference. Similarly, from phi Y to phi B, it has 120, and phi B to phi R, it has 120. Whereas the phi R is a reference and the direction of rotation is anti-clockwise. By considering phi R as a reference, phi Y lags phi R at an angle of 120 degree, phi B lags phi R at an angle of 120 plus 120 to 40 degree. Or else you can also say it as phi B leads phi R at an angle of 120 degree. So that the reference flux, that is instantaneous flux, you can write it as phi R is given by phi M sine omega t. Similarly, phi Y you can write phi M sine omega t minus 120 degree. Phi Y lags phi R at an angle of 120 degree. Similarly, phi B you can write phi M sine omega t minus 240 degree if phi B lags phi R at an angle of 240 degree, or you can write here it as phi M sine omega t plus 120 degree. So now you need to consider three cases for these three equations, that is phi R and phi Y and phi B. You need to check by changing the direction of this field phi R, phi B, phi Y, whether the resultant flux is constant or not. That you need to check. That is called rotating magnetic field. So that if for the first case, for case 1, if theta equals to 0 or omega t equals to 0 degree, you need to substitute the value of omega t in this equation. That is nothing but for the first case, phi R equals to phi M sine 0 is nothing but 0, and phi Y equals phi m sine 0 minus 120 degree is nothing but sine minus 120 minus root 3 by 2. Similarly, phi b you can rewrite here phi m sine 0 minus 240 degree or else 0 plus 240 degree. You can get plus root 3 by 2. See now, phi r equals to 0, phi y equals to minus root 3 by 2 times of phi m, and phi b equals to plus root 3 by 2 times of phi m. Whereas phi y is 0, so that you are not considering any phi r equals to 0. But by adding these two, phi r and phi y, sorry, phi y and phi b, you just observe earlier the phasor diagram will be like this: phi r, phi y, phi b. So now for the first case, phi r is 0, so that you're not considering this phase line. But phi y and phi b, the total resultant flux phi is given by phi r plus phi y plus phi b. That's nothing but 0 plus phi y plus phi b. But you have what? Phi y is nothing but minus root 3 by 2 times of phi m. It is nothing but minus phi y you have. You want to get plus phi y, so that you need to draw antiphase with this minus phi y. You can get plus phi y like this. See now, phi b plus phi y. Then you have to do what? Phasor addition. From the tip of phi b, draw a line which is parallel to phi y, and from the tip of phi y, draw a line which is parallel to phi b. Then you can get resultant flux, that is total flux by adding these phi y and phi b. Phi and the angles, you can see angle between phi r to phi b is 120 degree, whereas this will be divided as 60 degree and 60 degree, so that these angles are 30 degree and 30 degree. So by adding these two, we can get 1.5 times of phi m. That is nothing but, so now we have to draw a bisector or a perpendicular bisector that should cut the total resultant line equally half and half, so that this becomes pi by 2 and this will be pi by 2. So now we define cos 30 degree, so that cos 30 degree equals to, by considering this triangle OAB, A by H, adjacent divided by hypotenuse, so that you can write adjacent side is nothing but OA and hypotenuse is nothing but OB, OA divided by OB. OA is nothing but pi by 2 and OB is nothing but root 3 by 2 times of pi m, and cos 30 is nothing but root 3 by 2, so that root 3 by 2 equals to pi divided by pi by 2 divided by root 3 by 2 times of pi m. By solving this, by simplifying this, you can get total flux phi equals to 1.5 times of pi m for the first case. So like that, you have to do it for case 2 also. So when omega t equals to 60 degree and when omega t equals to 120 degree, so like that you have to do. Okay, so that you have to explain only 2 cases. Okay, so rotating magnetic field for 6 marks, 2 cases. So now move on to the problem. So there is one problem in a 3-phase induction motor with 4 poles supplied from alternators, which means that there is a motor which is supplied from alternator. So alternator and motor which are coupled together, alternator and motor which are coupled together, and this motor, induction motor, which is supplied from alternator. Whereas this motor is having 4 poles, a 3-phase induction motor with 4 poles, so that Pm is 4, from alternator having 6 poles, that is nothing but PA is having 6 poles, and this alternator running at 1000 rpm, that is 1000 rpm. Alternator which always runs at synchronous speed, so that 1000 rpm is ns of alternator. They asked you to find synchronous speed of motor and rotor speed of motor, and also when slip equals to, when s equals to 0.04, you need to find. Then You need to find the frequency of rotor Fr when n equals to 600 rpm for this case. So first case, you see, to find the synchronous speed of induction motor, you know that ns is given by 120 f divided by poles of motor, but frequency they are not given. So this frequency you need to calculate with the help of alternator. Whereas you know the alternator poles, alternator speed, so that you know that ns for alternator is given by 120 f divided by pa, so that frequency f you can get it as NSA into PA divided by 120. It is nothing but 1000 into 6 divided by 120. Okay, so you can get frequency as 1000 into 6 divided by 120. You can get frequency of 50 hertz. 50 hertz frequency you will get. So this you need to substitute here to get the value of ns. So now substitute the value of frequency. Frequency for alternator and motor which is same. There is no change in frequency. So that from the data from alternator, you are finding the value of frequency. Then you are substituting that frequency to the data of motor to get the value of synchronous speed. So that ns of motor is given by 120 into frequency is 50 divided by pm is 4. You can get 1500 rpm synchronous speed of motor. The first case finished, synchronous speed 1500. And what they asked in the second case, they asked you to find a rotor speed, that is nothing but n you need to find when s equals to 0.04 and ns equals to 1500 rpm. So you can rewrite now, n is given by ns into 1 minus s. So ns you know 1500 into 1 minus 0.04. You can get n that should be less than synchronous speed. So that 1500 into 1 minus 0.04. You can get 1440 rpm. 1440 rpm synchronous speed. So, sorry, motor speed. Synchronous speed is 1500. You need to find the value of frequency. Substitute, you can get ns, then you will get n. At last, they asked you to find frequency of rotor current. You need to find the value of frequency of rotor current when speed is 600 rpm. So that just write it here. So you need to find the value of, write it here. Shall we change? Okay. For n equals to last case, for n equals to 600 rpm, you need to find the value of frequency of rotor current. So frequency of rotor current is given by Fr equals to S into F, but S you don't know. To find S, they are given the N. So S is given by Ns minus N divided by Ns. Whereas Ns you already know it won't change. 1500 into N is 600 minus 600 divided by 1500. You can get S. So that 1500 minus 600 divided by 1500 can get 0.6. The slip value is 0.6. Then you can get the value of frequency of rotor current. Fr equals to S into F. That is nothing but 0.6 into 50. You can get 30 hertz is the frequency of rotor. The problem is very simple. First, you need to find the value of ns of motor, whereas this motor which is driven by alternator, so that with the help of alternator data, find the value of frequency, then substitute the value of frequency to get the synchronous speed of motor. Then with the help of synchronous speed of motor and slip, they are given 0.04. So are finding the value of motor speed n equals to ns into 1 minus s. Then they change the case now. You need to find the Fr when speed n equals to 600. If speed changes, speed of the motor which changes, slip also changes, so that you need to find the value of slip again. for n equals to 600 rpm, then you will be finding the while slip as a 0.6. By substituting that, you can get the frequency of rotor 30 hertz. This much you have to write. Okay. So if you are having any doubts regarding this, feel free to write in a comment box. And if you really like this video, please do subscribe. Thank you. Thank you so much. Have a nice day.